Hello and welcome to my channel. Today I will show you the cargo bins which are used to store the orders in my robot, from design to production. Hope you remember that I'm building an autonomous delivery robot for indoor delivery service. The bins I plan to create will be used to store drinks, snacks, and maybe some other small stuff. But before jumping into the bins creation, I want to share a stupid mistake I made while designing the charging station for my robot. Look, I placed the robot power switch right in the front of charging port. So when the robot is driving down to the charging station a bit faster than needed, the power switch hits its front panel, and that leads us to an epic fail. The whole robot powers off of cause. Luckily, we can fix that quite easily. I designed a new enclosure for the charging port with a properly sized hole in front of the switch. So now my robot can get in full contact with the charging port without getting into a trouble. Now the bins. Let's dig into bin design details, and I will show you the pipeline I use to break it into parts when I need to print a big part, which does not fit into my 3D printer's build volume. Here you see one of the 4 bins, the way it looks as a whole. Typically, there is a basic functionality in the software which is shipped together with your 3D printer to split an object. But it doesn't work for most of my cases. The parts I print are typically flat and curved pieces of plastic 2 to 3 millimeters thick. They should fit and glue to each other properly with a good adhesion. It is impossible to get all that done using a connection strip with 2 to 3 millimeter width. So I split the model during the design. So I splitted this bin into 3 parts: rear, front, and front panel. Here is a trick I do to make a proper connection between such parts. On the rear one, I chamfer both edges along the whole connection side for 1.5 millimeters. This part thickness is 3 millimeters. Then I cut this sharp feature from the front parts, and here you go. A marvelous joint. Adhesion surface became much bigger. Parts will align perfectly. The connection between them will be much stronger. It is much easier with the front panel though. I just create a flange which fits into its place on the front part of the bin. Next, let's print all those bin parts one by one. A year or so ago, I switched to Bamboo Lab Carbon X1 for 3D printing at home. I had a lot of 3D printers in my life. The first one was a wooden chassis MakerBot. It was long time ago. Then I had 2 generations of MakerBot with a steel chassis. I had an Ultimaker. With all that experience behind, Bamboo Lab is probably the best 3D printing thing which happened in my life. Because it just prints. It prints anything I ask it to print. I love AMS, which makes changing materials much easier. I love their plastic, despite the fact that it is more expensive than most of others. It's not an advertising, and I'm not paid by Bamboo Labs. This is just my personal opinion. Let's assemble one of the bins, just to get the idea of how it works. I glue together front and rear parts. I use a regular super glue from Kudo. It works fine for all the different types of plastics I use: PLA, ABS, and PETG. Then I glue the front panel to the bin. Now I use screws to mount brackets to the bottom of the bin, which will then be used to mount the sliders, and a bracket for the linear actuator which will move the bin. Why did I use screws here, not the glue? Because the sliders I bought have very imprecise drawings, and I couldn't exactly model where to place the actuator to fit bin into robot enclosure when closed. To make all this adjustable, I need to be able to easily change those brackets. A simple linear actuator I'll be using to move the bins. It's from AliExpress, 24 volts, maximum extension of 200 millimeters with speed of 30 millimeters per second. If you're interested in learning more details about any of the components I'm using, feel free to ask in the comments. Don't forget to subscribe to my channel. It motivates me to create new videos about the things I'm building. Let's have a look at the controller that will manage the actuators. I designed the schematic and routed the board in EasyEDA, manufactured the board at JLC PCB, and soldered it myself. I originally made this controller for a previous project, a delivery rover, which I've covered in many videos on my channel. The heart of the controller is the Raspberry Pi Pico. I mostly used STM32 microcontrollers in my projects, but I've been curious about this RP2040 microcontroller for a while. It's quite interesting. The board has a dual-channel driver for controlling regular motors, which will manage the linear actuators. Each channel of the driver is equipped with an INA219 current and voltage sensor. This allows for detecting jams or other issues in the actuator's movement. I've also routed a serial port, I2C bus, 3 outputs for controlling addressable LED strips, and a CAN interface based on the MCP2515. Why CAN? Because I hate having too many wires, and I really like using a bus for managing peripherals in a robot. When designing this controller, I had to choose which protocol to use over the CAN bus. There were various options, including creating something custom, but then I came across Drone CAN. This protocol was developed for communication between different components of a drone. It features strict message serialization, and there are many ready-made devices available. For example, I use one for battery monitoring in my robots. Overall, I liked it and decided to implement it in my controller. One mistake I regret: terminal blocks. Sometimes it's very inconvenient when you need to disconnect and reconnect something. I'll definitely switch to connectors in the future. These niches are where the bins will be placed. First, I'm installing the controllers, one for every 2 bins. Wires with connectors for the actuators are routed out. Now I'm installing the inside panels. They will shield the robot's internals from the user and also provide mounting points for the rails. Now we're installing the linear actuators that will move the bins. Next, we need to fully extend them forward so they can be attached to the bins. Of course, behind the scenes, there's all the work of writing the code. I build robots using ROS. A separate ROS node acts as a gateway between the Drone CAN bus and ROS, forwarding messages from the bus and publishing services that, for example, allow moving the actuators. Right now, I'm moving them using this service. The final stage of assembly is installing the bins into their places. I had to come up with this special tool to reach the latches that secure the rails. Since the rails are recessed inside the robot, it would be impossible to remove the drawers from the rails without this tool, if needed. I've secured the actuators to the bins, and now let's try moving the bins themselves. Here they are. Closing, opening, and overall, the entire mechanism works. I designed and 3D printed this cup holder to ensure the cups fit snugly but easily into it. Let's place the holder in the bin and test how well the cups stay in place. Voila! Hopefully nothing will spill during movement, but the drawers shouldn't leak, so I'm hopeful that no liquid will get inside the robot. Let's wrap it up. Today, I showed how to create large parts from 3D printed components, explained the design of the robot's sliding drawers, the controller that manages them, what actually moves them, and how everything is assembled. In the next video, I plan to show how the perception systems of my robot work. I hope you'll find it interesting. If you enjoyed this, don't forget to subscribe to my channel, and see you next time.